Hey guys, today we're gonna talk a little bit about calorimetry. What is calorimetry? How does it work? This jumps into several different concepts related to transfer of heat and clicks into enthalpy as well, which is what we've been talking about. But without any further ado, let's jump into this. Share screen, share screen, share screen with the students so they can learn the chemistry. Okay, cool. All right, let's get a brush going. See how it looks. Good. All righty. Okay. All right. So, first things first, I make sure that. Okay, cool. All right. So, what we're gonna do today is we're gonna identify a couple of different key concepts here. We're gonna talk about what exactly is calorimetry. We're gonna discuss the concept of specific heat. And then we're going to talk about how we can use calorimetry to measure changes of enthalpy of a system, right? So we've been talking at this point, excuse me, we've been talking at this point about how we have a system, right? And we have these surroundings. And then the system, if we do some kind of chemical reaction, right, the system can either be releasing heat into the surroundings, that would be an exothermic reaction with a negative delta H, or it can be absorbing stuff from the surroundings. There we go. Or it can be absorbing stuff from the surroundings, in which case it is an endothermic reaction with a positive delta H. Okay. Now, this is all very well and good, but the important part of calorimetry is that it's a way of identifying the changes in enthalpy for a system. Okay, a way of figuring out, let's say I have a system that I'm working with, and I know that there has to be some change of enthalpy, but I don't know what it is, exactly how many kilojoules are being released, exactly how many kilojoules are being absorbed. We don't really know that just by looking at the material, right? So what we have to do is we have to have a way of measuring how much heat is being absorbed or released by the system. How much heat is being absorbed or released by the system. And that's where we get into calorimetry. So our definition for calorimetry, it's going to be calorimetry. So this is, if you wanted to put a fine definition on it, is the measurement of heat produced or absorbed by a system. This would be enthalpy, change in enthalpy, using a calorimeter. What's a calorimeter? We're going to jump into that in a second. There's a couple of different versions. That's what calorimetry is, okay? The measurement of heat produced or absorbed by a system. This would be the change of enthalpy ultimately, right? And we use a calorimeter for this purpose. Okay, so in order to understand calorimetry, there's a couple other concepts I want to click in first. The first is one called heat capacity, right? So heat capacity represented by capital C. Actually, you know what? Let me make another text box for this too, because I feel like that is more helpful. I'll put all of my definitions over here. So heat capacity by C. So this is the heat required to raise a temperature of a sample by 1 degree Kelvin. Okay, the amount of heat required to raise the temperature of a sample by 1 degree Kelvin. Okay, so if I have some sample, let's say it's a 20-gram sample, let's say it's a 20 mole sample, that amount doesn't matter. The heat capacity of that sample is the amount of heat required in order to raise the temperature of that sample by 1 degree Kelvin. Okay, this is a common theme of the amount required to raise the temperature by 1 degree. That's a common theme. We're going to see that again here in a second, especially in the context of something called specific heat. Specific heat. This is represented by C and then subscript S. I think I can do this. Let's see if I can add a subscript. Oops. Nope, I cannot. So yeah, that means C with a subscript of S, right? So this is similar type of thing. The amount of heat required to increase 1 gram of substance by 1 degree Kelvin. So whereas the heat capacity represents there's not a set mass associated with heat capacity. It's just if I have a sample, how much energy do I need in order to increase it by 1 degree Kelvin, right? The specific heat is more specific, right? So it's the amount of heat required to raise 1 gram of a substance by 1 degree Kelvin. So for example, let's say that I have, oh, I don't know, a gram of iron. And then I have a gram of water. Because of the chemical properties of iron versus water, right? Each of them have different sensitivities to heat, right? Each of them are able to resist changes in heat without changing their own temperature. So they have depending on the type of substance that you're working with, they have different resistances to heat, right? And so as a result, it would take more energy for one than it would take for the other to increase the temperature by 1. Sorry, I kind of butchered that sentence. Let me try this again. So let's say that I had 10 joules of energy and I plugged that into H2O, and then I also plugged it into iron. The change in temperature, the increase in temperature, right, would be different for each of these, right? So the delta T here would not equal the delta T for the iron, right? Because they're just different substances. Okay, so that specific heat is the amount of heat required to increase 1 gram of a thing by 1 degree Kelvin. Broad strokes here, if I have a large specific heat, right, that means that it is resistant to heat or resistant to temperature change. Why? Because that means that in order to increase the temperature of the thing, I have to inject a large amount of energy, right? On the flip side, if I have a low specific heat, that means I am not resistant or have low resistance to temperature change. Okay? And the reason being that the low specific heat tells me that I only need a tiny amount of energy in order to start increasing the temperature of that thing. Okay? So that's our first concept, specific heat. The higher the number, the more resistant it is to temperature change. The lower the number, the less resistance you are to temperature change. Now, the specific heat, we can solve for the specific heat using an equation, right? So the specific heat is equal to the quantity of the heat transferred, which we represent by Q. You may recall Q as being heat transfer from this equation. Delta E is equal to Q plus W. Okay, so Q in this case is the heat transfer. Right? And then we divide that by the mass of the substance in grams. And then the change in temperature. Now, importantly, this change of temperature has to be in Kelvin. Has to be in Kelvin. But luckily, the change of temperature, right, because since Celsius and Kelvin are the differences in each individual degree are the same, the change of temperature, the delta T for Celsius is actually going to equal the delta T in Kelvin. So as well, there'll be some instances later where you have to convert something into Kelvin. As long as you know what the change of temperature is in Celsius, you know what the change of temperature is in Kelvin as well. Okay, so if we plug all these things together, right, then we can solve for our specific heat. What's really useful with this is we can rearrange this question or this equation in order to solve for the amount of heat transfer. So if I just bring the m and the delta T over here to the specific heat side, and I just rewrite like this, Q is equal to MCAT. For all of those who want to go to medical school, this is a particularly triggering equation. So if I take the mass and I multiply it by the specific heat and I multiply it by the change in temperature, I can measure the heat transfer. I can measure the heat transfer. And this is where this starts to click into calorimetry. Okay, because remember, enthalpy, right, at a constant pressure, we talked about this a little while ago, enthalpy is equal to this guy right here. It's equal to the heat transfer given a constant pressure. Okay, and so what we want to do is if we have a system, let's move back up here. If we have a system that we're working with and we know its mass and we know its specific heat and we know its change in temperature, we can figure out how much energy it's absorbing or releasing. Okay. And that's what the purpose of calorimetry is. It's utilizing something like the specific heat and the mass and the change of temperature of a thing in order to calculate out how much energy it's either releasing or absorbing. So, without any further preamble, we can finally start talking about actual calorimetry here. So I'm going to scroll down a little bit here. And again, I'll always send you guys this image, and then you can take screenshots as you wish. So what does a calorimeter look like? So the way this works, there's a couple different forms, but usually what you're going to do is you're going to have some container in here, and there's going to be some medium in the middle. We like to use water, but you can use ethanol. You can use whatever type of medium you want, right? But you want to have a thermometer measuring the change in temperature of the medium. We'll see why in a second. Then what you do is you're going to have some kind of chemical reaction going on down here. Okay. And sometimes it could just be something as simple as you take a flaming hot chunk of iron and you put it in the bottom of this container, and the chemical reaction is it radiating heat, right? Releasing energy, right? Okay, so this is fantastic. We have a way now of measuring the change in the temperature here, right? Whenever we're doing this, right, we usually want to know the specific heat of the thing we're working with, right? And the specific heat of the surrounding medium. Okay. We'll also want to know the mass of the medium. I'll put another subscript here to indicate what we need. So the mass of the medium, the specific heat of the medium, the specific heat of the, let's call it the sample. And maybe if we can figure out the mass of the sample, that'd be great too. But essentially, we want to learn as much as we can about these two portions, the medium that's surrounding the sample and then the sample itself. Okay. Now, the way that we're, again, just to try and drive home what we're doing here. When we're doing calorimetry, what we're going to do is we're going to measure changes in the surroundings, right? So this medium that we're talking about, we're going to measure changes in the enthalpy of the surroundings, and we're going to utilize that as a way of figuring out stuff about our sample, right? Now, the reason we can do this has to do, or it hinges on this assumption that the change in the heat transfer of the system is equal to the negative change in the heat transfer of the surroundings. What does that mean? Well, this means that if I do this reaction, since the medium that we're working with, right, since the medium we're working with is totally surrounding our sample, right, that any change of heat, right, from this sample has to result in a change of enthalpy for the surroundings as well. So for example, let's say that it's releasing heat, right? It has to release that heat somewhere, and the thing that that's the thing that's surrounding it is this water or other medium. So that means that the loss of heat of this system is going to result in an increase in heat of the surroundings. And the converse is true. If this system has to be absorbing heat in order for it to work, it has to absorb the heat from somewhere, and the medium is the only thing that it's coming in contact with, so that heat has to be extracted from the medium. So for this reason, the heat transfer in the system is equal to the negative heat transfer of the surroundings. Okay. So again, just to make it as obvious as I can, if the system is releasing heat, right? If the Q of the system is minus, then that means that the Q of the surroundings has to be positive. If the Q of the system is positive, that means that the Q of the surroundings has to be negative. Okay. Now, we're going to try and do this step by step. So let's say we had a cup of water that's about 150 grams, right? And that's going to be our medium. So we have a cup of water. Let's say this is 150 grams. Okay. Inside the cup, we have a chemical reaction going. The chemical reaction results in an increase of temperature of 5 degrees Celsius. Okay. So that means that our change in temperature, it's getting higher. So it's plus 5 degrees Celsius. Okay. The specific heat for water, this will be something that would be given to you, is 4.184. And this should be, I always forget what the units of this are. Give me 1 second, guys. Or at least the organization. Yeah, joules per gram Kelvin. Okay, so now what I want you to do with these guys, and take a second, you can pause the video if you want, is figure out, okay, this is what we know about the surroundings. What is the change of enthalpy of the system? What is the change of enthalpy of the system? Now, the way we would solve this, right, is we would go back to our equation from up here, Q equals MCAT, right? We're solving for the change of enthalpy, Q, of the surroundings, right? Because I've given you stuff related to the surroundings. Our mass here is 150. Our specific heat is 4.184. And our change in temperature is 5. Okay. Now, if I grab my calculator from somewhere and plug all this together, right, so what I just did, guys, all I did is I just plugged and chugged with the Q equals MCAT equation. So 150, yikes, times 5 times 4.184. That gives me a Q of 3,138 joules. Now, that is the Q of the surroundings, okay? The Q of the surroundings, right? The reason why it's the Q of the surroundings is each of these variables that I'm plugging in, these relate to specifically the surroundings. They have nothing to do with the system at this point, okay? Or let me phrase that. None of these variables are coming from the system. These are all changes to the surroundings. And from this, we glean that the Q is equal to plus 3138 joules. What that means then in plain speak is that this water absorbed 3,138 joules of energy. Now that has to be coming from somewhere. And if you recall, the Q of the system is equal to the minus Q of the surroundings. So in order to figure out what the change of enthalpy for the system is, all I have to do is switch the sign. So if Q of the surroundings is 3138, then that means that Q of the system is the exact same number, but with a different sign, minus 3138. Okay? So this system is releasing energy. Why? Because it has a minus number, a minus Q, right? So that means it's releasing energy in the form of heat transfer, right? And that amount is 3138. Now you could ask, all right, is it possible there's no true perfect system surroundings. So is it possible that some heat is released into the environment? Yes, it is possible. Within chemistry, you're trying to minimize that as much as humanly possible. And you can assume for the purposes of question that no heat is being lost to the exterior of our medium, right? Just if you work with this equation, that works for me. Okay, so now based off of this we can start to infer stuff about the system. Remember that the Q attaches to several other things. We can learn about the mass, we can learn about the specific heat, we can learn about the change in temperature, right? So you can use the Q. Once you, essentially what you're doing here, just to reemphasize, is you're utilizing information about the surroundings to solve for the Q of the surroundings, use the Q of the surroundings to solve for the Q of the system, and then you use the Q of the system to solve for individual characteristics of the surroundings. So we can start to piece this together into a protocol. Let's do this right. Meow. So to solve for, the way this typically shows up is you're solving for mass. Mass of system. Mass of system using calorimetry. Step one. Use Q equals M times, and you will have this equation for the exam. Delta T to solve for Q of surroundings. The thing that trips folks up here is they will inevitably take mass of the system or specific heat of the system or change of temperature of the system and try and plug it into this first one. The first step is super important because you're trying to figure out the change of enthalpy for the surroundings first. So what's the mass of the water? What's the specific heat of the water? What's the change of temperature of the water? So use this first one to solve for Q surroundings, right? Step number 2, flip the sign of Q of surroundings to make it Q of system. Okay, so if you have a minus, it becomes a plus. If you have a plus, it becomes a minus. And then use this specifically for mass, rearrange the equation to solve for mass. That looks like M equals Q divided by CS times delta T. Okay. Now, this is specifically how to solve for mass of a system. You can do the exact same thing, right, to solve for the specific heat or the change in temperature. Note that what's always going to happen is you're going to leave your variable of interest on one side, and you're going to divide the enthalpy by the other two variables. So if I'm looking for mass, I divide the enthalpy by specific heat and change of temperature. If I'm looking for specific heat, I divide enthalpy by mass and change of temperature. Okay. So this same way of doing it can be used to determine the unknown, whether it be mass, specific heat, or change of temperature. Okay. So there's our protocol. And let's go ahead and do that for this last step. So let's say that we have, so our Q of our system is negative 3138. Let's say, wait a minute, is that what I said? Yeah, 3138. Let's say that the energy is coming from a flaming hot block of aluminum. The aluminum has a specific heat of, let's see, 0.9 joules per gram Kelvin. And the temperature has decreased by 100 degrees Celsius. Now, this is another thing that trips people up. If you have temperature increase, that's going to be a plus number. If you have a temperature decrease, that's going to equal a minus number. Okay. Either way, if you end up with minus grams, you've done something wrong. You flipped your sign, right? It's impossible to have negative mass, at least in this universe. Okay, so now what I'm figuring out is, how do I solve for the mass? So the question is, how do I solve for mass? So I have my Q of my system. Now I have my minus number here, right? I have my specific heat and I have my change in temperature. So what I can do then is to solve for mass. We know that mass is equal to Q over CS times delta T. So minus 3138 joules divided by my specific heat, which is 0.9, times my change in temperature, which is minus 100. Just as a check, the sign of your Q should be the same sign as your change in temperature, right? Because otherwise you end up with minus mass or whatever. So if I do all this, Excuse me. So 31 divided by 0.9 times 100. Cool. Then I should end up with, all things being equal, I should end up with 34.9. Where's my little cursor? 34.9 grams. Okay. So that's what calorimetry is. It is a way of taking information. Let me try and contextualize this real quick. It's a way of taking information. We're taking information about the surroundings, using that information in order to figure out the change of enthalpy of the surroundings, using that understanding to know about the change of enthalpy of the system, and then using that change of enthalpy of the system as a way of figuring out characteristics of the system. Okay? This is a common question that people have. You can expect to have a question like this on any exam I give you, where I'll ask for something like mass. Sometimes I'll ask for something like specific heat. But yeah, that's basically what calorimetry do. There's something else called bomb calorimetry, which is, we could talk about that another time. Maybe we'll discuss that in lecture. But as far as basic calorimetry is concerned, this is the main concept that I want you guys to be picking up. Okay, that's all I have for you guys today. I'll be sure to bring worksheets into lab, and we can go through a whole bunch of stuff focused on calorimetry. But other than that, see you guys later. Okay, buddy.